Hello, my name is MD Abdul Shabuz. I have recently defended my dissertation in chemical engineering from Mississippi State University. I welcome and thank you for your interest in our work. We can assure you that you will learn something new from our findings. Today, we will share our work on open shell donor-pi-acceptor conjugated metal-free dyes for dye-sensitized solar cells, where we have found that a small dye-radical character can significantly redshift the absorption maxima in the near infrared region. Our article recently made the front cover of MSDE journal. You can read our article this whole month without any charges. Before going deeper into the presentation, we will first look at some terminologies which will make the presentation more interesting. First, let's look at the definition of open shell dye-radical molecule. Molecules containing an unpaired electron are called monoradicals, free radicals, or simply radicals. However, the definition for open shell dye-radical is a little bit tricky. An open shell molecule where two electrons occupy two different regions in space rather than in the same point as in the closed shell can be termed as dye-radical if it's in the neutral state. It has two unpaired electrons which can be aligned either anti-parallel to each other in the singlet state or parallel to each other in the triplet state. And the unpaired electrons occupy two different but energetically degenerate or near degenerate molecular orbitals. Another term we will encounter is the singlet triplet energy gap delta EST, which is the energetic difference between a singlet state and a triplet state, where S is the total spin. We need a parameter that can more quantitatively describe the open shell dye-radical character. Theoretically, the occupation number of the lowest unoccupied natural orbital is proposed to be a measure of dye-radical character. The dye-radical index defines how much open shell character a molecule has developed. For ordinary closed shell molecules, all the LUNO occupancies are close to zero, describing a perfectly coupled electron pair. This high electron coupling can be seen from this large shaded region with a very high Coulomb repulsion because the two negative charges are at the same place, which will also increase the singlet triplet energy gap. In a pure dye-radical, the LUNO occupancies are close to 1, describing a perfectly uncoupled electron pair and obviously a reduced Coulomb repulsion than the closed shell configuration. In the intermediate dye-radicaloid situation, the dye-radical index varies in between 0 and 1 with a reduced electron coupling and a Coulomb repulsion than the closed shell molecule. Now let's jump to the main part of the presentation. It is said that the world energy demand will increase by about 70% between 2000 and 2030, whereas EIA predicts about 50% increase by 2050, as can be seen from this bar plot. This ever-increasing need for energy compels the scientific community to search for renewable energy sources. Dye-sensitized solar cells are an attractive alternative energy source due to their excellent durability, cleaner environmental footprint, and the ability to tune the photosensitizer to absorb light in a particular region of the solar spectrum. Let's first look at how a dye-sensitized solar cell works. The important parts of a DSC are the dyes, which is a critical component of the device that absorbs photons from the sunlight, a semiconductor surface, a counter electrode, and the redox shuttle. In a DSC device, the dye absorbs photon and goes into an excited state. The photoexcited dye ejects an electron to the conduction band of a metal semiconductor such as titanium dioxide and get oxidized. The electron is then passed through an external circuit and being collected by a counter electrode. Finally, the electron gets back to the oxidized dye by a redox shuttle, regenerating dye and the cycle repeats. The power conversion efficiency of the DSC largely depends on the dye and its ability to absorb low energy photons in the near infrared region. It was found that designing a dye which can absorb light around 940 nanometer can increase the current of DSC by 40%. This motivates us to design DSC dyes which can intensely absorb light in the NIR region. Despite significant past effort in designing dye sensitizers, the large energy gap between the frontier molecular orbitals of most available dyes prohibits the absorption of low energy photons. Thus, most of the photons are wasted as heat. Almost half of the total energy transferred through the sunlight is in the NIR region. Therefore, tailoring dye molecular structure to absorb enough photons in the NIR region is of particular interest to increase the power conversion efficiency of DSC device. There are different approaches to design metal-free NIR dyes. The rate shift in the absorption wavelength is achieved by extension of the pi system and connecting an electron-rich donor with electron-deficient acceptor unit together. However, majority of the dyes designed by this approach have large homolume energy gap, prohibiting NIR absorption. Another interesting approach is to use open shell diradical dyes. Although a significant amount of works have been performed on molecular-based diradicals, however, there is no evidence of open shell diradical dyes particularly designed for DSC device. So, how much open shell character is necessary in DSC dyes? We will answer this question a little bit later. Let's just keep in mind for the time being. The power conversion efficiency of a DSC is calculated using this equation. To increase the power conversion efficiency, we need to increase the open circuit voltage, short circuit current, and the fill factor. Here, we will mainly focus on the DSC parameter, which is directly related to the dye, and other two important parameters such as the electron injection efficiency and dye regeneration efficiency. As indicated in this figure, the DSC parameter is inversely related to the homolume energy gap. Now, to increase the DSC parameter, we need to reduce the homolume energy gap. However, there is one problem in doing that, which is a sweet dilemma in DSC device. A very low energy gap diminishes the driving force for electron injection and dye regeneration, which limits the short circuit current density as well, because the DSC parameter is directly related to these two parameters. One of the objectives of this work is to find an optimal diradical character which can provide a good balance between different factors affecting the power conversion efficiencies in DSC, which will answer the question we have posted before. Here we have reported open shell diradical dyes for DSC device and correlate their electronic and optical properties with diradical character. In this regard, we have designed donor-pi and acceptor dyes by modifying the structure of conventional dye D35. The choice of D35 is based on the fact that this dye is extensively used in DSC device and it provides ample opportunities to modulate molecular geometry. In particular, we have replaced the thiophene pi spacer of D35 with BBT and ISO BBT spacer. Also, the electronic properties are further tuned by placing thiophene, thionothiophene, and nitrogen on the molecular backbone. As can be seen from this figure, the BBT-based dyes with thiophene and thionothiophene spacer develop open shell diradical character, which is due to the fact that the BBT spacer has a high HOMO and lower LUMO energy level than the ISO BBT spacer, which reduces the homolume energy gap and facilitates admixing of frontier molecular orbital in the ground state. Also, the thiodiazole units of BBT recovers aromatic stabilization energy in the open shell ground stage, which also facilitates developing a diradical character. The open shell dyes significantly reduce the singlet triplet energy gaps. Materials with a small singlet triplet gap are good candidates for singlet fission process, which can increase the power conversion efficiency of solar cells from theoretical Shockley coaxial limit of 32% to 45%. There are certain design criteria that needs to satisfy in case of an ideal dye. The HOMO needs to be well below the redox shuttle oxidation potential, and the LUMO must be above the conduction band of titanium dioxide surface, which will provide sufficient regeneration and injection efficiencies. As can be seen from this figure, all the design dyes satisfy this criteria. However, as we increase the dielectrical character, we can see a reduction in the injection and dye regeneration efficiencies, which limits the dielectrical character to be below 0.10 as a design rule. To get the absorption spectra, first we have performed benchmark calculation on the parent dye D35 to select an appropriate functional. The absorption maxima predicted with MO6 2x functional is very close to the experimental value in ethanol solvent. Therefore, all the excited state properties are calculated with MO6 functional in implicit ethanol solvent. The absorption spectra of the parent and design dyes are provided in this figure. As we can see from this figure that all the design dyes significantly redshift the absorption maxima from the parent dye D35. However, the open shell dyes have a more redshifted absorption maxima than the closed shell dyes, such as comparing the absorption maxima of open shell dye MS3 with its closely related closed shell dye MS9. We can see that the open shell dye redshift the absorption maxima by 570 nanometer, whereas the closed shell dye only redshift the absorption maxima by 99 nanometer from the parent dye D35. In case of the open shell dye, the singly occupied molecular orbitals are delocalized over the whole backbone of the molecules, which ensure the thermodynamic stability of the open shell dyes. Also, the spin density distribution indicates the unpaired electrons are delocalized over the whole pi framework, which will also increase the stability of the open shell dyes. The prominent intermolecular charge transfer character of these dyes are clearly visible from the density difference plots, as can be seen from this figure. The intermolecular charge transfer is observed from the TPA donor to the cyanocyclic acceptor and part of the pi spacer adjacent to the acceptor unit. This indicates a good charge separation in all the design dye is obtained, which will also facilitate redshift in the absorption spectra. The takeaway messages from the presentation are: a small amount of dielectrical character redshift the absorption maxima. Design rule is to develop a small dielectrical character for DSC dye. Also, a delocalized orbital topology of open shell dye will increase the thermodynamic stability in the DSC device. We would like to thank NSF for financial support and HPC2 for computational resources. We also acknowledge the developers of different software we have used in the project, especially to Gaussian 16 software project with which all the calculations have been performed. Also, we thank to our group members who directly or indirectly helped in the project. Thank you for your attention and investing your time listening to this presentation. And please don't hesitate to contact us if you have any questions.